Hey, this is Chemical Bonding 1. These are the topics that we're going to talk about. So elements tend to gain, lose, or share electrons in order to acquire a full octet, like the noble gases. So a maximum of 2 electrons can be held in a single orbital. N equals 1, the first energy level only has 1 orbital, so a full octet is only 2 electrons. Expanded and reduced octets are exceptions to the octet rule. Some of the elements from N equals 2 to N equals 6 can acquire fewer or more than 8 valence electrons, and we'll look at those in the next video. In ionic bonding, like I said, elements lose or gain electrons in order to acquire the electron configuration of the noble gases. So metals lose electrons to form positive ions, and nonmetals gain electrons to form negative ions. So metals are to the left of the staircase, nonmetals are the right, and ions can also be polyatomic, right? Ammonium NH4 plus is the only nonmetal polyatomic cation that you'll need to know. You can predict the charge of most ions from the group that they belong to on the periodic table, so we labeled these in pre-AP. So group 1 is +1, group 2 is +2, group 3 metals +3, but thallium can do a +1 charge. It may only lose its electron from the p orbital, producing a +1 charge. Group 4 produce +4 ions, but tin and lead can also produce +2 ions, because sometimes they only lose the two electrons from their outer p orbitals. All group 5a nonmetals produce electrons with a -3 charge. Group 5a metals form ions with +3, +5 charges. Group 6 produce ions with a -2 charge, and polonium produces ions with a +4, +2 charge. And the halogens have a -1 charge. So D-block cations, these ions don't always follow the octet rule, and many of the transitional metals don't form ions at all. So this is why you have to be told the charge when you're naming. You can form solid salt crystals by mixing solid sodium metal with chlorine gas. So this is an exothermic reaction where electrons are transferred from sodium to chlorine, and they stick together due to their opposite electromagnetic charges. You can also form salt by distilling or boiling off the water from salt water. Here the ions have already lost or gained electrons, and the water evaporates the ions. They become more attracted to one another and they stick back together. So later we'll learn about how those ions are attracted to the polar water molecules and they are to each other. But when you get rid of the water, they rebond. So ionic bonding, an electron is transferred from sodium to chlorine. This produces a positive and a negative ion, both with full octets. The oppositely charged ions will then stick together due to electrostatic attraction. And this is a very exothermic process. Ionic compounds exist in crystal lattice structures. So salt doesn't exist as a single NaCl unit. So it forms a cubic structure where every sodium ion is surrounded by 6 chlorine ions, and every chlorine ion is surrounded by 6 sodium ions. So you have to inject a lot of energy to break a lattice containing 1 mole of sodium chloride formula units into 1 mole of sodium and into 1 mole of chlorine. So part of the reason why it requires so much energy is due to the fact that each ion is attracted to 6 other ions of opposite charge. So from Coulomb's equation, we can see that melting point increases as the charge of the ions increase, it's your numerator, and the distance between the ions decreases, your denominator. So you need to be able to use this equation to make predictions about the melting points of different ionic compounds. The stronger the force of attraction between ions, the higher the melting point. And this formula is not given on your formula sheet on the AP exam, so you have to know it. When making predictions about melting point, you need to look at the charge of the ions and the size of the ions. Greater charges always are more significant than a difference in size. So here, lithium fluoride or lithium iodide, which one would have the greatest melting point and why? Lithium fluoride is smaller than I. So that means lithium iodide would have, lithium fluoride would have a greater melting point. Magnesium chloride or magnesium oxide, which one? So here we need to look at their charges since they're the same side. Magnesium has a +2 charge, chlorine is a -1 charge, whereas magnesium has a +2 charge and oxygen has a -2 charge. So magnesium oxide would have a greater melting point. Sodium fluoride or magnesium iodide. So greater charges are always more significant than a smaller distance. So magnesium iodide has a higher melting point. Example 2. Which of the following metal fluorides would have the highest melting point? So the F ion is the red ion. The fluoride always carries a -1 charge. Since the ions in both of these compounds are in a 1-to-1 ratio, both cations carry a +1 charge. The compound containing the cation with the smallest radius will have the highest melting point. So B would have the higher melting point because the charges are +1, -1 for both compounds. But the metal cation has a smaller radius. So you'll have to answer questions like this in the AP exam, and you'll also have to explain why one ion is smaller than another. Properties of ionic solids. So it takes a lot of energy to break apart ionic crystal lattices. You have to add a lot of heat to get them to melt. Ionic compounds are considered to have an extremely low volatility, as it takes an incredible amount of energy to break the ionic bonds and allow ions to enter the gas phase. They'll usually break to form surfaces with definite angles to one another as the ions they're lined up in repetitive patterns. And the brittleness tends to result from repulsion of like charges as one layer slides over another. This is why ionic compounds are not malleable or ductile. Solubility and conductivity. A simple test for determining if water contains ions is to run electricity through it. One can also determine if a non-conducting solid is ionic by dissolving it in distilled water and seeing if it conducts electricity. Right? So you'd electrocute yourself if you dropped the hairdryer in a bathtub because the ions in the tap water conduct the electricity. Distilled water has a very limited ability to carry electricity, like only 1 in a million water molecules dissociate to form the hydrogen and hydroxide ions. So ionic compounds tend to dissolve in water because of the attraction between the cations, and the positive ends of the water molecules are stronger than those between the cations and the anions, and the attractions between the anions and the negative ends of the water molecules are stronger than those between the cations and the anions. Ionic compounds don't dissolve in nonpolar solvents, as attraction between the ions are higher than the attractions between ions and nonpolar solvent molecules. Covalent bonds. So in covalent bonding, electrons aren't transferred from one another, they're shared. The electron density from the valence electrons of both atoms increase between the two nuclei. Both nuclei, positively charged, are attracted to the electron density, which is negatively charged. So what is electronegativity? It's an element's ability to attract electrons in a chemical bond. The greater the electronegativity value associated with a particular atom in a molecule, the more strongly it attracts itself. The electrons attract it to itself. Electrons spend more time around the atom with a higher electronegativity. Electronegativity difference is obtained by just subtracting the electronegativity values of the two atoms that are bonded together. And if this difference is 0, the bond is completely covalent. And most chemists will still consider a bond to be covalent if the electronegativity difference is 0.5 or less. Completely covalent means that the electrons spend an equal amount of time around each atom. This is actually only true if the two atoms have the same electronegativity value, like oxygen is completely covalent and is diatomic, right? So polar covalent means electrons spend more time around the more electronegative atom. It's a polar as the bond has a net positive and a net negative end, like the poles of a magnet. The greater the electronegativity difference, the more polar the bond. Not all chemists agree on the upper value where a bond goes from being polar covalent to ionic, so it generally ranges from like 1.7 to 2. A bond is considered to be completely ionic when the electronegativity value is about 3.5. Electrons are not considered to be shared in ionic bonds. So some ionic compounds of aluminum have polar covalent bonds, like aluminum and sulfur. So types of bonds. These balloons represent the electron density distribution. So fluorine is perfectly covalent. The electrons are evenly distributed around the two fluorine atoms. So your electronegativity difference here is 0. In the HF molecule, the blue region represents low electron density, and the green region represents high electron density. So the electrons spend most of the time around fluorine. The fluorine atom develops a partially negative charge, and the hydrogen atom develops a partially positive charge. So for all diatomic molecules, these charges are equal and opposite, and so they're completely covalent. In the NAF molecule, the electron was donated from sodium to fluorine, so it spends all of its time around the fluorine atom. And electronegativity values are unitless. Right? So polar covalent bonds, the atoms, like a summary, the atom with a higher electronegativity develops a partial negative charge as the valence electrons from both atoms spend more time around it. The atom with a lower electronegativity develops a partial positive charge, which is in equal magnitude to the partial negative charge of the more electronegative atom. These partial charges increase as electronegativity differences increase, and the sum of the partial charges in any molecule or ion is always equal to the overall charge on the species. Alright, so determining bond type. So here it's diatomic, the electronegativity difference would be 0, so it's nonpolar covalent. Here the electronegativity difference is 0.4, so it's considered to be nonpolar covalent. And HBr, electronegativity difference is 0.7, so this would be polar covalent. CO2, polar covalent. LIF, ionic. All right, molecular compounds. In pre-AP, we call these covalent compounds. They call them molecular compounds on the AP exam. They mean the same thing. So two or more nonmetals bonded together to form a compound, and these are going to be nonpolar or polar covalent. Polyatomic ions, a combination of nonmetals or metals, and nonmetals bonded together to form a polyatomic ion. And again, these bonds are still nonpolar or polar covalent. So we'll only use these for covalent compounds, the Lewis structures, and they'll provide a visual representation of the location of the atoms and the relative distribution of electrons. And you have to know how to do these in order to predict the shape. And we'll predict shapes next lecture, but if you can't draw Lewis structures, you won't be able to predict molecular shape. Alright, so here are the steps. Step 1, count the total number of valence electrons. Put the least electronegative atom in the center and connect terminal atoms to it with single bonds, except for hydrogen. He can't ever go in the middle. Step 3, complete the octets for all terminal atoms except for hydrogen. Step 4, add the electrons you have used and subtract from the total number of valence electrons, and attach leftover electrons to the central atom as lone pairs. Okay, so let's do CO2. We're going to count up the number of valence electrons, so 16. Carbon's going to go in the middle because it's the least electronegative. Complete your octet. Okay, now here we don't have any extra electrons, so carbon's octet is not full, so now we need a step 5, where we're going to make multiple bonds to complete the octet of the central atom. If there is an oxygen atom in the structure, make it a double bond before you make anything else a double bond. Okay, so we're going to put double bonds on our oxygen. Double lines indicate a double bond, triple lines a triple bond, single bonds. Alright. In some cases you may need to make a triple bond, and that's okay. If you're making a Lewis structure with a polyatomic ion, you must take the overall charge of the ion into consideration. So polyatomic ions have gained extra electrons, well, except for ammonium, right? So the overall charges aren't neutral, so you have to add the total number of electrons they've gained to your valence total. Alright, try these in class and we'll go over them.